Hello friends, we learn the chapter Oscillations here. Now in this chapter we study the energy of particle performing simple harmonic motion. We know what is the simple harmonic motion. That is, the simple harmonic motion is periodic motion, it is oscillatory motion. The particle oscillates about to and fro about its mean position and the motion is periodic, hence it is simple harmonic motion. Now we find the energy of particle performing SHM in this case. Now consider the particle here. Consider the particle is at point P. O is the mean position here. It starts from here point O and reaches to point B at a distance x. Now this is the distance x. It is the displacement. Now OM represents the extreme position. Again ON represents the extreme position in negative side. Now here we consider the particle performs simple harmonic motion about the mean position. Now let consider the particle is at point A, is at point P at a distance x from the mean position. Therefore, it oscillates or it performs linear simple harmonic motion. In this case, the velocity of this particle is given by the formula V is equal to omega under root a square minus x square. Now see, when the particle performs the simple harmonic motion, it having the velocity at mean position it is maximum and the velocity at extreme position it is minimum. Now so that we can say that when the particle oscillates about this mean position, it having the energy, and this energy, that is, it have a velocity, thus it is moving, therefore it having a kinetic energy. That is, in this case we can say that, or when the particle performs simple harmonic motion, it regains the energy due to motion. It is the potential, it is the kinetic energy. Now when particle is at extreme position, it reaches to extreme position, then it tries to move, it is towards mean position. Due to restoring force. Therefore, there are two types of energy involved. In this case, the first is kinetic energy and second is potential energy. See, consider the particle performing simple harmonic motion about this linear or along the straight line. Now suppose the particle P, it is at point P at a distance x and this is the displacement x. Now when the particle it is at OM, it is at extreme position. Suppose the particle is at N, it is having extreme position. Here we consider particle is at point P. We find the energy at point P here. See, at mean position the velocity is maximum, at extreme position velocity is minimum. Here particle have a velocity, therefore there is a kinetic energy. Now the suppose particle is at extreme position, due to it restores or the restoring force acting on it and it having the potential energy. Therefore the total energy in SHM is equal to kinetic energy plus potential energy. Why there is kinetic energy in this case? See, at mean position particle having maximum velocity, due to motion there is a kinetic energy. Now suppose the particle is at extreme position and it tries to move towards mean position, it have a restoring force therefore it having a potential energy. Thus total energy is sum of kinetic energy and potential energy. Therefore we first find the kinetic energy, then find the potential energy, addition gives the total energy. Total energy is sum of kinetic energy and potential energy. Now consider expression for kinetic energy. Expression for kinetic energy. We find the kinetic energy of a particle. Now, when the particle performs simple harmonic motion, the velocity of the particle is given by the velocity of the particle. It is maximum at mean position, and the magnitude of velocity is given by magnitude of velocity is given by the formula, that is V is equal to omega. It is plus or minus omega under root a square minus x square, but here we consider only magnitude, therefore V is equal to omega under root a square minus x square, where V is linear velocity, omega is angular velocity, a is amplitude, x is the displacement. Now here see, suppose this is the distance x, that is it is the displacement. Now suppose particle is at here, that is at extreme position. What is the amplitude here? The maximum displacement from mean position, it is called as amplitude. Now the velocity is given by V is equal to omega under root a square minus x square. Now we have the formula for kinetic energy. Kinetic energy is given by, kinetic energy is 1/2 mv square. 1/2 mv square. Kinetic energy is given by the formula 1/2 mv square, where m is the mass of particle and v is the velocity of the particle. Now substitute the value of velocity here, that is under root omega under root a square minus x square bracket square. Then we get the value 1/2 m omega square in bracket a square minus x square, which is the value of kinetic energy when the particle performs simple harmonic motion. Now in this case we have, or we substitute, suppose we substitute here, that is k is equal to m omega square, we get the expression for kinetic energy is 1/2 k into a square minus x square, k into a square minus x square. Suppose this is the equation number 1. This is the equation number 1. Now again we write the another expression for kinetic energy, that is we have the value, suppose V is equal to, we know we have the value of velocity, it is velocity is equal to, we know suppose x is equal to here a sin omega t plus phi. Then velocity is given by a omega cos omega t plus phi. Again we can find the value of kinetic energy here. Kinetic energy is given by here 1/2 mv square. Substitute the value of V in this case, we get m into a omega cos omega t plus phi bracket square. Then we get the value of kinetic energy. Kinetic energy is equal to m a square omega square cos square omega t plus phi here. Now see, we can write here m omega square, it is 1/2 k a square cos square omega t plus phi plus phi. We can write kinetic energy this equation also. Now we find the expression for potential energy. We find the value of potential energy. Therefore, expression for potential energy. Expression for potential energy. Now here we consider, see the particle is at point P and it is the distance at a distance x. Therefore, suppose the particle moves toward the extreme position, there is work done for this particle, and we know the restoring force. Suppose particle is at extreme position, the restoring force acting on the particle, and the restoring force is given by F is equal to minus kx. F is equal to minus kx. That is the condition for simple harmonic motion. Now suppose dw be the work done if the particle moves through small distance dx. Therefore, work done is equal to, we can write work done is equal to here it is force multiplied by displacement. When force is here minus kx dx, and this work done and force, they are opposite, that is minus F, and substitute here, suppose F, it is minus F into dx, that is restoring force is opposite to the mean position. Substitute here minus kx into dx. Therefore, work done is equal to, here work done is equal to, that is dw is equal to, we can write force, that is kx dx. Now we have to find here total work done, that is integrate from the both side, integrating both sides. Integrating both sides, we get integration of dw is equal to integration of kx dx. Now the integration, the lower value, that is it varies from, displacement varies from 0 to x. Now integration of dw, it is w. Integration of dx is x, hence we can write integration of dw is w. Now see, suppose substitute the value, k is constant here, and integration of x dx. The values varies from 0 to x. The integration of x is by using the formula integration of x raised to n, it is equal to x raised to n plus 1 divided by n plus 1, it having the value, that is x square divided by 2. The lower limit is 0, upper limit is x. We can substitute here upper limit minus lower limit, it becomes kx square divided by 2, that is w is equal to 1/2 kx square. This potential energy is stored in the form of the potential energy, and the potential energy can be given by 1/2 kx square. Potential energy is 1/2 kx square. Now the total energy of the particle or the particle performing simple harmonic motion is given by total energy is equal to substitute the value of the potential energy and kinetic energy here, that is kinetic energy plus potential energy, which is equal to, kinetic energy is given by, suppose this is 1/2 k into a square minus x square plus 1/2 kx square. Then if we simplify, we get k a square minus 1/2 kx square plus 1/2 kx square. That is plus k square minus k square gets cancelled. We get 1/2 k a square. That is total energy is equal to 1/2 k a square. Now suppose we substitute the value of total energy here, we get, see, total energy is equal to 1/2 k a square. Substitute the value of k here, that is total energy is equal to 1/2 m omega square a square. This is the expression for total energy. This is the expression for total energy, or it is total energy, we can say total energy is directly proportional to omega square a square, directly proportional to m. Now here we substitute, suppose omega is equal to 2 pi n. Suppose substitute the value of omega, that is it is equal to 2 pi n, where omega is angular velocity, n is frequency here, we get 1/2 m into 2 pi n bracket square a square. Therefore it becomes 1/2 m 4 pi square n square a square. Now again we substitute the value of frequency here, that is it is 1/2 m 4 pi square, that is 1/t square a square. From this equation we can say that this total energy is directly proportional to mass of the particle. Then it is directly proportional to square of the frequency. It is directly proportional to square of the amplitude, and this total energy is directly proportional to or inversely proportional to square of the period. This is the dependence of total energy on mass, frequency, amplitude and period. Now this is the expression for total energy. Now we see some special cases. Case number 1. First, suppose the particle is at mean position. Mean position. The kinetic energy is given by, kinetic energy is equal to 1/2 omega square a square minus x square. And potential energy is 1/2 kx square. Now at mean position, value of x is equal to 0. Substitute the value in this case, we get kinetic energy is equal to 1/2 m omega square a square minus 0. It becomes 1/2 m omega square a square. That is kinetic energy is equal to 1/2 m omega square a square. Now suppose substitute the value of potential energy, that is at mean position it is 1/2 k x square, value of x is 0, that is it becomes 0. Potential energy is 0. At mean position. See, kinetic energy is equal to 1/2 m omega square a square and potential energy is 0. Now see, in this case at mean position potential energy is 0, and kinetic energy is 1/2 m omega square a square. Thus we can say that in case of or when the particle is at mean position, total energy is purely kinetic. Total energy is purely kinetic. At mean position, the total energy is purely kinetic. Now we consider the second case. Case number 2. Case number 2, that is kinetic energy, that is the particle is at extreme position, that is x is equal to plus or minus a, then again we have the value of kinetic energy. It is kinetic energy is equal to 1/2 omega square a square minus x square. Substitute the value of a here, x is equal to a, kinetic energy is equal to 1/2 m omega square a square minus a square. That is, it becomes 0. Kinetic energy at extreme position is equal to 0. Now substitute potential energy. We have potential energy is 1/2 kx square. Now potential energy is equal to, substitute the value of x here. It is 1/2 Ka square. That is, when the particle it is at extreme position, it is the kinetic energy at extreme position is 0 and potential energy is maximum. That is, at extreme position the total energy is entirely potential. Now see the figure. In this case we see, suppose the first case, in the first case, see here potential energy is 0. Now see, at mean position potential energy is 0, and kinetic energy, see kinetic energy is maximum here. That is, at mean position total energy is entirely kinetic. See again. At mean position potential energy is 0. At mean position potential energy is 0. At extreme position, or we can say that at extreme position, at that time potential energy is 0, kinetic energy is maximum, and we draw the graph like this. That is, at mean position total energy is entirely kinetic. Now in next case, in second case, that is when the particle is at extreme position, that is, see, when the particle is at extreme position, the kinetic energy is 0. The kinetic energy is 0 here. Kinetic energy is 0 and potential energy is maximum. The potential energy is maximum here, and at extreme position the total energy is entirely potential. In any other position the total energy is partly kinetic and partly potential. It is partly kinetic and partly potential. Now we see the next two cases. Suppose we consider here, if kinetic energy, third case, if kinetic energy is equal to potential energy, kinetic energy is equal to potential energy, what is the relation of the displacement and amplitude? We know kinetic energy is equal to, we have the formula, kinetic energy is equal to 1/2 m omega square a square minus x square is equal to, potential energy is given by 1/2 m omega square x square. Then 1/2 gets cancelled here, m gets cancelled, omega square is cancelled, omega square is cancelled here. Remaining part is a square minus x square is equal to x square, is equal to x square here. Now see, from this we can say that x is equal to a square is equal to, this becomes 2x square, 2x square. Therefore x square is equal to a square by 2, a square by 2, and x is equal to plus or minus a divided by root 2, a divided by root 2. That is, when kinetic energy is equal to potential energy, the displacement is plus or minus under root 2. Here we graphically shows that when kinetic energy and potential energy, they are equal, the displacements are plus or minus a divided by root 2, a divided by root 2. Now again we consider the last condition, that is, suppose the particle, suppose we consider here displacement is equal to plus or minus a by 2, a by 2. Now suppose kinetic energy is equal to potential energy, kinetic energy is equal to potential energy. We find the relation between the kinetic energy and potential energy by substituting the values. X is equal to plus or minus a divided by root 2, and it is kinetic energy is equal to 3 times potential energy, 3 times potential energy. Okay, thank you.